Dr. Yokoyama is a fellow of Fujitsu Laboratory. He received the 1998 Lieberman Award of IEEE for his work on gallium arsenide MOSFET. And he is now the leader of the Green Nanoelectronics Center in Japan's new National Institute of Advanced Industrial Science and Technology. He will speak to us about core technologies for green nanoelectronics. Let's welcome Dr. Yokoyama.
Thank you very much, Professor Hu, for your introduction. I'm Naoki Yokoyama. Good afternoon, ladies and gentlemen. Today, I would like to talk about development of core technologies for green nanoelectronics. This research was funded through the funding program for Innovative R&D on Science Technology, or FIRST FIRST program. This was recently initiated by the Council for Science and Technology Policy in Japan. So I would like to acknowledge all the people who are working for my first program, particularly Shintaro Sato and Mizuhisa Nihei for their contributions to the development of application of nanocarbon materials, and Toshimichi Shintani and Junji Tominaga for their contributions to material research for back-end devices. So in June 2009, presidents of University of Tsukuba, the National Institute for Material Science, and National Institute of Advanced Industrial Science and Technology, in cooperation with the chair of Committee on Industrial Technology of Japan Business Federation, Nippon Keidanren, announced the intention to establish a central R&D hub for nanotechnology in Tsukuba area. This was named Tsukuba Innovation Arena for Nanotechnology, or TIA Nano for short. The TIA Nano has started in April 2010 with 6 core research domains, including nanoelectronics, power electronics, NMEMS, nanogreen, carbon nanotubes, and nanomaterial safety, while providing 3 core infrastructures, including nano device research foundry, including 4,500 square meter super clean room, and nanotechnology open user facilities, and networking school of nanotechnology. In the core research domain of nanoelectronics, 4 national projects have initiated, and 3 of them are first program, namely development of core technologies for green nanoelectronics led by myself, and the ultra-low power spintronics-based logic VSIs led by Professor Ono of Tohoku University, who is one of the speakers at this symposium, and photonic electronics integration systems project led by Professor Arakawa of the University of Tokyo. The 4th program is super low voltage devices for low carbon society, which is sponsored by METI, Ministry of Economy, Trade and Industry. 4 projects have launched, gathering more than 100 researchers from industry, academia, and National Institute under the one roof, using the same facilities of 4,500 square meter super clean room space. And in my first program, about 30 corporate researchers from Renesas Electronics, Arbac, Fujitsu, Toshiba, and Hitachi, and 20 AIS researchers are getting together. So Dr. Sakamoto, who is also one of the speakers at this symposium, is working for this program. So I would like to introduce current status of this, my first program. So here is outline of my talk. First, I would like to introduce the background and R&D plans for Green Nanoelectronics project. Then I would like to describe our graphene growth technology and a top-down fabrication technology for graphene nanoribbons. And finally, I would like to introduce the latest hot news regarding interfacial phase-changing memory devices, which exhibits a giant magnetic resistance of over 200% at temperatures up to 400 Kelvin. So ICT society of 21st century is about to witness a new paradigm shift from computer-centric world to network-centric world and then to human-centric world. And such a society will provide personal security, safety, and social activities to everyone, resulting in a truly ubiquitous society. In such society, individuals are provided with anytime, anywhere access to desired information. So future ICT will need to meet people's requirements more precisely and become more user-friendly and reliable. However, developing such a society merely by extending current technologies would greatly increase the power consumption of ICT equipment, such as network devices, displays, and storage and servers. This is because the fact that internet traffic is expected to exceed 120 Tbps in 2025 in Japan. That is 190 times that in 2006. So the power consumption of ICT equipment is predicted by METI to be 240 billion kilowatt hour in 2025, which is 5.2 times that in 2006. This power is comparable with that total electric power generated by nuclear power in Japan before the big earthquake. So a paradigm shift in ICT society could result in environmental destruction. So to solve this problem and develop an environmentally friendly ICT society, technological innovations for reducing the power consumption of ICT equipment are needed. So here you see an image of 10 petaflops supercomputer systems called K, which was jointly designed by Japan's Riken Research Institute and Fujitsu. This system contains 800 racks of computing gear, housing 80,000 Fujitsu Spark 64 FX processors running at 2.2 gigahertz. The processors are interconnected with a high-capacity direct connection network that enables fast communication between neighbors. The K system, which was partially operational, was ranked at the top in the latest top 500 supercomputers list. And also the K system was one of the most energy efficient systems in the list. So this system is now fully installed and it will be fully operational in 2012. So this figure illustrates the progress of Spark 64 series by plotting a peak performance using blue bars and power using red bars for each generation. So this performance has been improved by using scaled-down semiconductor technology from 130 to 45 nanometers, as well as using a merge core processor with increased number of cores from 1 to 8. So Spark 64 SFX processors were designed for the use in supercomputers using large instruction set architecture, the highly integrated systems on chip, and water cooling for high reliability. So the speed was faster than previous, 3 times faster than the previous generation, while power dissipation was reduced by half, being rated at 2.2 gigaflops per watt. So note that supply voltage remained constant at 1.0 volt for all these processors in the Spark 64 series. This is because that it is very difficult to reduce the supply voltage of CMOS LSIs. So to reduce the power consumption of the computer by another order of magnitude, we may need to reduce the supply voltage to a half or less of its current value. So the first goal of my project is to develop low voltage operation CMOS devices by using high mobility 3-5 and germanium materials for the channel of CMOS devices, aiming at operation at less than 0.4 volts. And further, a goal is to develop core technologies for demonstrating the feasibility of graphene transistors and new operation principle FET, such as tunneling FET and impact ionization FET, aiming at operation of less than 0.2 volts. The second goal of our project is to develop growth and application technologies for nanocarbon materials, to develop low resistance three-dimensional interconnections using carbon nanotubes and graphene for low voltage operation of the LSIs. And our dream is to develop all carbon green nanoelectronics by developing transistors, carbon nanotube memory, and heat management and packaging. The third goal is to develop back-end devices such as non-volatile switches and memories made from new materials embedded in wiring layers and providing low power operation of LSIs with increased functionality of wiring layers. The first example is three-terminal atomic switches, which function at low voltages, which is applicable to reconfigurable logic. Dr. Sakamoto will be giving us a talk on these devices. And second example is much valued magnetic tunneling junction memories, which is applicable to low power and high speed embedded memory. The third example is low power chalcogen superlattice phase change memory for next generation non-volatile data storage. So METI program, led by Dr. Sumihiro from NEC, is seeking to develop these three kinds of devices using 300 millimeter wafer line, aiming for practical applications. And therefore, my program is focusing on fundamental research of new materials for application to chalcogen superlattice phase change memory devices. So next, I'd like to describe our graphene growth and the top-down fabrication of graphene nanoribbons technology. We are using thermal CVD to grow graphene films using ion catalyst film. Here you see a cross-sectional TEM image of 32 nanometer thick and 7 nanometer thick graphene films, and mostly bilayer graphene. So this figure plots the thickness of multilayer graphene as a function of the product of pressure and the growth time. So thickness appears to be proportional to the square root of the product of pressure and growth time. This until to 50 nanometers. This indicates that we can grow the multilayer graphene with controlled thickness for application to interconnections. So we are currently focusing on the improvement of quality of graphene, and also we are developing the technology to connect graphene layers with carbon nanotube beads. We are also trying to grow graphene film on a 200 millimeter silicon wafer coated with copper catalyst film. Here you see Raman spectra measured at positions A, B, C, D, and E. A D band is hardly visible. And this is a cross-sectional TEM image of this sample, indicating that mostly monolayer graphene is grown. So we think this monolayer graphene can be used for transistor application. This figure shows binary phase shift keying modulator that we propose as one of examples of application of graphene transistor. We fabricated graphene transistor by using mechanical exfoliation onto P plus silicon substrate coated with silicon dioxide insulator film. The FET has both top gate and back gate electrodes. And this FET exhibited the clear Dirac point with unbipolar characteristics, meaning that the FET exhibits N-type characteristics for positive substrate bias and P-type for negative gate bias. So this is a circuit configuration of a modulator. So binary digital data and a sinusoidal carrier wave are input to the back gate and top gate respectively. And as is shown in this measured waveform, output voltage is inverted or not inverted depending on the level of digital input. So inversion means the phase shift of pi. Digital data can switch the phase between pi and 0. So phase modulation concept are widely used as a modern standard in digital wireless communication systems such as mobile phones and digital TV broadcasting. However, for digital and logic application, we have to create the band gap. So there are two main techniques for band gap generation. One is to make graphene nano ribbon, or GNR. Another is to use bilayer graphene under vertical high electric field. There are two approaches for GNR fabrication, bottom-up approach and a top-down approach. For bottom-up approach, we are developing self-organizing technology for GNRs by using preferential growth on high-index surfaces of copper. Also, we are trying to synthesize GNRs with chemical process in collaboration with universities. So I would like to describe our top-down nanotechnology. We use helium-ion microscope in fabrication of GNRs. The first advantage of using helium-ion is that we can realize high-precision etching because of smaller beam size than electron beam, because the double-eye wavelength of helium is smaller than that of electron. In addition, direct etching of graphene without resistor mask enables high pressure etching because there is no edge roughness due to a resistor mask. And the second advantage of using helium ion is that we can avoid any contamination from resist process because direct etching of graphene is possible. Thus, helium-ion beam etching seems to be ideal for GNR fabrication. However, on-off operation of current has not been realized yet. So we try to demonstrate on-off switch of current by fabricating GNR with our helium-ion microscope. The process is very simple. First, we exfoliate the single-layer graphene from HOPG to silicon substrate coated with 300 nanometer silicon dioxide layer by using famous Scotch tape. And then we made source drain contacts by using conventional lithography. And then we checked and we confirmed the FET exhibits Dirac point with unbipolar characteristics. Then we fabricated GNR by direct etching using helium-ion beam. This process was completed on March 10th, which is just before the day of the big earthquake in Japan. So 2 months after, we measured this sample. So this sample survived for 2 months after a big earthquake. And here you see an image taken by the same helium-ion microscope. A dark region is the area where the graphene was etched off. And this schematic is enlargement of this portion, indicating that 5 nanometer wide and 50 nanometer long GNRs was fabricated. This figure shows on-off operation by backgate bias. This figure plots the drain current in logarithmic scale, measured as function of backgate bias, with a parameter of drain voltage at 45K. So on-off switch about 2 orders of magnitude was observed. Here you see a linear scale plot of the curve measured at 1 millivolt drain voltage and indicating clear transport gap over 10 volts of backgate bias. From this value, we estimated that transport gap is around 200 millielectron volts, which is comparable that calculated using this empirical equation proposed by Dye's group at Stanford University. This indicates we could make GNR without serious damage at the edge or near the edge of nanoribbon. So next, I would like to introduce the latest hot news about interfacial phase-change memory devices. Phase-change random access memory, or PCRAM, is very promising for the next generation non-volatile data storage. The PCRAM devices encode the data as structural changes between disordered and crystalline states in a film of tellurium-based alloy materials, such as germany, antimony, tellurium, consuming useless energy due to entropic losses for structural changes. So Dr. Tominaga, who is now the member of my project, proposed using germanium, tellurium, and antimony 2 tellurium-3 superlattice materials to reduce power consumption for switching. In this superlattice structure, switching between low resistivity and high resistivity can be achieved by displacing germanium atoms at the interfaces by applying electrical voltage pulses. So during this process, superlattice crystalline is reserved, while coordination number of germanium atoms switches between 6 and 4. Since entropic losses are reduced for this process, power dissipation for switching it can be greatly reduced by 1 order or 2 order of magnitude. So this was published in Nature more recently. The superlattice PCM is now referred to as interfacial phase-change memory, or IPCM, because interfaces between germanium, tellurium, and antimony 2 tellurium-3 plays an important role for controlling the switching of germanium atoms. This figure compares the read resistance measured as a function of dynamic pulse current between conventional and IPCM materials. Note that direct current to reset the phase from low resistivity to high resistivity state is greatly reduced for IPCM from 50 milliamps to 1.5 milliamps, resulting in power reduction by an order of magnitude. Since germanium, antimony, tellurium alloys do not have a magnetic moment, magnetism was not thought to play a role in its switching dynamics or electrical properties. However, Tominaga of AIST hit an idea that applying a magnetic field to IPCM might affect the material properties. Since antimony 2 tellurium-3 was reported to be a topological insulator by Professor Lin of Northwestern University. So this is because an in-plane external magnetic field is expected to further contribute to the splitting in spin states induced by the Rashba effect at the interfaces. So this figure compares the switching behavior of alloy device and identical composition IPCM device with and without magnetic field in plane of 0.1 Tesla. So IV characteristics measured for alloy device was insensitive to the magnetic field. The IV characteristics of IPCM device without magnetic field was very similar to that of alloy device, and showing the set voltage or threshold voltage of 0.85 volts. However, the threshold voltage increases 2.0 volts when you apply magnetic field. So over the voltage from 1 to 2 volts, magneto resistance was 100%, and temperature up to 400 Kelvin. So honestly, we are currently unable to explain these experiment results completely, but this finding paves the way for development of conceptually new memory devices that combine the merits of both phase change and magnetic data storage.
Excuse me, it looks like it's 200%. Or
100%.
But it's...
This is, these are low resistance state, and this is high resistance.
Oh.
So by calculating delta R becomes 20. Actually, 100% magnetic resistance was observed already, but now we are checking. Okay, so this is a paper by Tominaga and others of my team, published in Applied Fixed Data, latest Applied Fixed Data. So if you are interested in finding out more details, please read this paper and directly contact Dr. Tominaga at this address. Okay. So such green nanoelectronics technology is likely to be used in many applications in addition to energy saving of IT equipment. The application will include information terminal that works with solar cells, and wearable and implantable medical devices powered by ambient energy, or autonomous robot and others that work in housework, support, nursing, and hazard locations. And another important aspect of green nanoelectronics is to provide education system where people can learn about nanotechnology through industrial academic collaboration in its core innovation arena. So since our objective and R&D plans for green nanoelectronics seem to be quite similar to those of the energy efficient electronic system program, I anticipate there will be greater information exchange between them so that we can accelerate our research together to realize energy saving and human-centric ICT societies. Thank you very much for your attention.
Questions for Dr. Yukon?
Are you also looking into energy harvesting side of devices, like some devices where you can actually generate energy instead of...
I'm sorry, I couldn't follow the question.
Energy harvesting devices. Are you also looking at energy scavenging, energy harvesting?
Harvesting energy, you mean? So you mean why I don't include the harvesting technology, you mean? Yeah, I would like to include such a research, but my budget is limited, so I can't do it.
Okay, I wonder if you could explain why the antimony telluride, being a topological insulator, would move the switching point of the phase change out when the magnetic field is being applied.
So you mean what's the mechanism of
Yes, what's the mechanism?
So we are currently investigating, but we have already observed German motion by using the facility of spring rate. I mean, there are 2 tellurium atoms, and then germanium looks like penetrate between them. And so coordination number changed from 6 and 4. And the energy required to move is about 2.3 electron volts. So by applying electric voltage and as well as current, we can switch them.
And the role of the magnetic field is?
Yeah.
And the role of the magnetic field?
Also, by applying the magnetic field in plane, through the spin orbital coupling, effectively applied to electric field perpendicular to the, which will induce spin current of the topological nature, at the interface between antimony to tellurium-3 and germanium tellurium. So we are currently investigating the magneto-optical properties, and also we are calculating the band diagram of this material, and we would like to confirm the existence of spin current. So it's a very interesting area.
Yes, very interesting.
One last question.
In the conventional PCM, they're applying heat to change the crystal versus amorphous state, right? So here, you don't think heat is required anymore. You just apply electrical voltage and magnetic field and change the state.
Could you repeat the question?
In the interest of time, I would suggest that you discuss with the speaker separately.
Okay.
Thank you.
Thank you very much.